Okay, so in today's lab, we are working on experiment 7, which is electron configuration and periodic properties. So in this case, we're going to see a clear link between the arrangement of electrons in our atoms and an observable property, such as atomic radius or the emission spectra, the color that is observed when a sample is heated in a flame or exposed to an electric current. Okay, so you're going to want to read through the manual page for experiment 7. So just to show everyone where that is, if we go to Vital Source, which is where I house all the textbooks for, or where I access my ebook version for this text. If you have a different source, that's perfectly fine. So you'd open up your lab manual and you'd go to lab number 7 titled Electron Configuration and Periodic Properties. Is everyone able to find this lab in their lab manual?
So we skipped atoms and elements?
Yes.
Okay, thank you.
In the schedule, I have sometimes 2 labs listed because one of them is a potential dry lab I can assign. But for this week, we're just going to be focusing on lab 7. So that's the lab pages that I want you to read. I also would recommend that you look through your chapter 2 notes and the workbook pages. And so in this lab, what we're going to be looking at is the relationship between electron configuration, how electrons are arranged in different orbitals, and the energy of our electrons, and the light emitted, the color of light emitted when samples are exposed to a flame. We call this a flame test. So you may want to read chapter 4 before attempting this laboratory. Chapter 4 also has a bunch of information relevant to electron configurations, orbital energy diagrams, and flame tests. Now, the central feature, the central part of this experiment that we're going to look at is emission spectra. So to talk a little bit about light for a moment, light is part of the electromagnetic spectrum, and different wavelengths and energies associated with light appear to our eyes as different colors. So the different colors of light will have different wavelengths and different energy. Again, this is lab 7, just to make sure everyone's on the same page. Now, as we discussed in lecture, electrons have a discrete energy. Electrons have a discrete energy. And as a result, when an atom gains energy, we can promote our electron to a higher energy level. So when our atom gains energy, that in turn leads to our electron moving between energy levels. Now, the really, really cool part here, and the part that we can actually see, the part that we can observe visually, even with the naked eye, is that when the atom relaxes back to its ground state, when the electron returns to its lower energy state, the atom will release light. And this light will have a unique color associated with it. And we can observe the color of light emitted as our sample is heated, gains energy, and then its electrons relax back down to the ground state. And this color of light is unique for each element. Does that make sense to everyone? So an atom gains energy when we heat it. The electron goes up to a higher energy level. It then drops back down and we observe light emitted. And in this experiment, we're going to observe the color of light and we're going to use it to identify the element found in a sample. To think of a more practical, to think of some cases where you've seen this in your day-to-day life to help you visualize and help you understand examples of emission spectra in your day-to-day life. If you look behind me, if you look behind me up here, you may see a light in the background. We have plenty of lights throughout our homes and throughout the cities that we live in. And each of those lights, the old school lights would function by this principle where they would heat a sample, and then as the sample electrons relax back down to the ground state, they'll release light that we can see. So this is an example of emission spectra that we observe in our day-to-day lives. Does that make sense to everyone? Does everyone understand the idea behind emission spectra and how it's unique for each element? So these notes are mentioned in the lab, but I also have these notes present in the Canvas page for Lab 7. And that's what I'm talking and lecturing from right now. Does that make sense? Perfect. So this recording is also going to be saved and posted on Canvas as well for your reference. So let's clear this drawing and let's continue on and let's talk a little bit about electron configurations. One comment that I have for the electron configurations is I'd like you to wait on this section until you've either read the textbook or until we finish the lecture on Monday, because we'll be doing a lot of examples on electron configurations on Monday. So this part, you can wait for the lab until Monday because we're going to be doing a ton of examples in your notes. So really make sure to attend lecture on Monday for the electron configuration part of our talk. So this is more information on periodic table arrangement and electron configurations. We'll talk a lot about this in lecture on Monday, and I've assigned this lab preemptively, so that way once you've looked over the lab, you have some problems that we're going to talk about in our lecture that directly match the lab problem. For periodic trends, again, we'll talk about the periodic trends portion of this lab in lecture on Monday. So in terms of what we're doing practically in this experiment, in terms of what we're focusing on for this experiment, what we're doing today is we're going to be looking at part A of our lab, which is flame tests. You're going to watch the following videos and you're going to record your observations in table A2. So if you go to your lab manual, table A2 is found right here. Let me pull up the exact page. Here we go. So we have different solutions, different metals present in these solutions, and we're going to observe the color of the flame. So each of these videos showcase the tests for different metals. You're going to need to watch and pay close attention to each of these two videos as they have flame test results for each of these metal ions. So for example, let's pretend we're watching this video. They're going to talk for a little bit, and then finally they're going to start the flame test. So in the flame test, what they're going to do is they're going to light the flame. They're going to then immerse their sample into the solution, and then they're going to observe the color when the sample is heated in a flame. We're exciting the atoms found in our solution. We're exciting the electrons present in our metal cation. The electrons will change in energy, and when they drop back down, the atom will release light. And we can observe the color of light and match it directly to the identity of our atom. So in the first part, you may want to turn on closed captioning. So they're looking at calcium chloride, CaCl2, which is something that you need. You can also see it from the picture. They're looking at calcium chloride. And now I just want you to watch what happens in the video. Just watch this first part together with me. What color do you see? What color do we see?
Red.
Red, yep, exactly, exactly. And that's what you're gonna write down in your observations. And try to make your observations as discrete as possible for the different emission, the different flame test colors, because even those two elements may both be red, they may have different small hues, small differences. So you'll repeat this process for all of your element samples until you've completely filled out this table of 6 elements. Does that make sense? Is that clear to everyone on what we're doing for the first part?
Show me the exact table. I can see it. I cannot find the table you showed me.
In table A2, it's on page of your lab manual. Let me find the page number. It should be on page 82 of your lab manual.
Okay, the one oxygen. Oh.
Were you able to find that page?
May you see the table one more time?
Yes.
Okay. Yeah, mine is a different page. Okay, I found it.
Okay, perfect, perfect.
Okay.
So once you've collected your data for the known sample, so the lab is titled Electron Configuration and Periodic Properties, and this is the results table that you're filling out in that lab.
So for the first video, do we fill that in for part A2?
So both of these videos together will have all the elements found in A2. You'll have to watch both of the videos, as the first video doesn't have all of the elements. So the second video is a supplement, which has some repeats, and it also has some new elements that are not mentioned in the first video. Does that make sense? So
Yes, thank you.
just to be 100% clear, this first video doesn't have barium, so you're going to need to find the barium results in the second video. So both of these videos have the pieces that you need to take all of your flame test observations. Does that make sense?
Yes, thank you.
Mm-hmm. So once you have the data from each of the 2 provided videos, you're then going to look at these 3 unknowns where I've provided you a table for unknown 1, 2, and 3. You're going to fill that in for part A3. You're going to record from my tables that I provided the color of the flame. And then you're going to identify each of your unknowns, each of these 3 unknowns, as one of your known samples by comparing your unknown flame color to your known flame colors. Does that make sense?
So in the little boxes, it's just 1, 2, and 3, and then the colors.
Yep, exactly. And your job is to compare the color for your known sample with your unknown sample, and then to assign the element in your unknown. Does that make sense?
Yes.
Perfect, perfect. You're then gonna, yes, how can,
Circles, what are those circles on the number 1 on the lab manual? It's spot plate out.
you don't have to worry about those circles. This would just be a diagram if you are actually preparing those solutions.
Okay.
So in part B, for electron configurations, part B, I would wait until we finish lecture on Monday. For part B, you're gonna write the electron configuration, valence electrons, and group number for each atom in this table. We will do a lot of examples like this in lecture, and in fact, some of these atoms we'll do in lecture on Monday. So save this table, just make a note that in my chapter 2 notes that we're going over on Monday, this is what we'll be doing. So make sure to save that. Part B, you'll be working on, and we'll be working on that partially in the lecture on Monday. Part C is atomic radius. So you're given in part C, you're given this graph of atomic radius versus atomic number. So in the lab manual, you're given the atomic number and the atomic radius in this table in part C. What you're gonna do is you're gonna graph this data on the following piece of graph paper in your lab notebook, and you're gonna use the completed graph to answer the questions in the report. So to give you an example, about what this would look like, for example, hydrogen has an atomic number of 1 and a radius of 37. Helium has an atomic number of 2 and a radius of 50. So what I'm going to do is I'm going to go to my chart and I'm going to fill in my data points. So my atomic number of 1 for hydrogen. So we know hydrogen has an atomic number of 1 and a radius of 37. Helium has an atomic number of 2 and a radius of 50. So I'm going to make my graph. I would recommend potentially trying out different increments. So I'm going to look and I'm going to go to my main data set and I'm going to try to figure out what my maximum and minimum is. It looks like my maximum radius is going to be around 200. So if I wanted to estimate, what range I would need, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So I have 25 boxes. And if my maximum value is about 230, I'm going to make each box worth 10. So that way I can include all my data points in my graph. So I'm going to fill in that portion of my graph. So now that I've filled that in, I'm going to include my data points now. So I'm going to plot my data points. So hydrogen, which has an atomic number of 1 and a radius of 37. So I'd plot that roughly right here. Helium has an atomic number of 2 and a radius of 50. So I'll plot that like here. And then to my plot, I'm going to add not a best fit line in this case, but instead just a trend line that connects each of my points. So it's not quite a best fit line. You're not trying to fit all of your data points to one line, but what you are trying to do is to monitor and capture trends in atomic radius. So you're graphing all of the points that have been provided in the table for part C, and then you're going to use that completed graph to answer the questions. Does that make sense?
Professor, I'm trying to open the table, but it doesn't open. I even refreshed my computer.
Yes, that's this table is it's telling you to reference the table in your lab manual.
I have the custom one. There is no numbers in here. I don't have the manual. I don't have those numbers.
Let me show you it. 1 minute. It should be on the earlier page in the procedure, part C, titled Atomic Radius. Are you able to find it on page 77?
Okay. It's page 57 on the custom edition.
Perfect.
Yeah, I found it. Thank you.
Perfect. So once you've completed your graph, then you'll be able to answer questions 4 and 5 that require your graph. So part C is relatively straightforward. Once you've answered all the questions and you've filled in the data tables for parts A, B, and C, that's all you'd need for today's laboratory.